So this lecture is the second part of the lecture on the third chapter of numerical method, resolution of systems of linear equations. So now we're going to look at the revision on metrics, which is the tool that's very important in numerical method. So I have to stress that there are several things that you need to have quite a strong background on it in order to be able to follow the course. So the first and foremost, because we get into these 2 points, are of course the physics of the nature that you're going to study or solve the equations. For example, if you're looking into a mechanical engineering type of problem of, let's say, for example, vibration problem or heat transfer problem, you need to know the fundamentals of heat transfer and vibration properly. What are the laws, the equations that involve, and what's the step in order for you to come out with the equations, because if you don't have the equations in the beginning, then this numerical method is not there to help you to come out with the equations. So numerical method is the tools that help you to find the solution, but the equation you have to provide it to it. So now in this part is the part of is the second layer, which is where we talk about the mathematical background that helps us in solving the equations. So the two main thing that you need to know properly is, of course, algebra, operations of algebra, because once you have your equations that is deduced from the problems of your physics, then you have to manipulate those equations. Then that needs algebra, right? And then the next thing that we're going to look at more in detail here is matrix notation and operation. So in numerical method, the methods use matrix form in order to find the solutions. So different methods manipulate matrix differently. So we need to really do revision on matrix, right? So matrix, we're going to go through this quickly. Matrix, so what's a matrix? Matrix is a rectangular array of elements represented by a single symbol. So for example, let's say now we have a matrix that's symbolized by symbol A, matrix A. It is, we say that matrix A is a matrix of a certain dimension with n numbers of rows and m numbers of columns. So here are the rows, right? Here are the rows. So here we can see 1, 2, 3 rows that can be seen. There's of course multiple more rows. That's what we call rows horizontally, and vertically is what we call the columns. So let's say here we say that A has a dimension of n by m, n the number of rows and m the number of columns. And then in matrix, there are the matrix that we're going to use is a square matrix. Why a square matrix? It is very important. Why? Because a square matrix would mean that you have the number of equations and the number of unknown that you have are equals. If you have 5 equations and 5 unknown, that means you would have a matrix with a dimension of 5 by 5. Or here it's a 4 by 4. It means it comes from a problem that have is a matrix that comes from a problem that have 4 unknowns and 4 equations, right? So it's always going to be a square matrix. So a square matrix, a 4 by 4 is this kinds of matrix. And the elements that is very important for us is what we call a principal, the principal or main diagonal. What is the principal? The principal or main diagonal are simply the diagonal element of the square matrix that is highlighted here in this blue circle. So in this square matrix, there are several configurations of matrix that you need to know the names, because later I'm going to recall the names. I want for you to transform the matrix into a certain configuration of matrix and into other configuration of matrix. So we have to know them. So the first one is what we call a symmetric matrix. Symmetric matrix is a matrix where when you look at your main principal or diagonal elements, the diagonal elements become the mirror for the right hand side elements and the left hand side elements. For example, here you have diagonal which is 5, 3, 8, and on both sides the elements have the same numbers. Here it's 1, 1, 2, 2, 7, 7, right? So that's symmetric matrix. Second one is what we call diagonal matrix. Diagonal matrix is a square matrix with The only element that is non-zero is the element on the diagonal here. Other than that, they are all zero. Next is what we call identity matrix. Identity matrix is very important. Identity matrix is basically a matrix that has the same dimension with the matrix of its identity. Let's say we have a matrix A of 4 by 4. And identity matrix to A is a matrix I of 4 by 4 with a diagonal element of 1, right? Other than that, it's 0. The only elements that is non-zero is diagonal, and they're equal to 1. That's what we call an identity matrix of 4 by 4, right? So what's special with identity matrix? I'm gonna explain later in operations of matrix, right? So the Q's are here, but I'm gonna explain later. And then next, so next, the other configuration of matrix that we also have to know their names are upper triangular matrix and lower triangular matrix. So upper triangular, lower triangular. Upper triangular matrix is a triangular that has non-zero elements only on the upper side of the diagonal. Lower triangular is a square matrix that has non-zero elements only on the lower side of the diagonal. And then the last one is what we call a banded matrix. Banded matrix are matrix that has non-zero elements besides the diagonal, in the row or in the elements that is next to the diagonal. For example, here we have the diagonal. The only non-zero elements are the one that is next to the diagonal. Other than that are 0. So here, for example, we have the diagonal and 2 elements, one to the left, one to the right. So 3 elements in the diagonal that is non-zero. It's what we call a 3-diagonal matrix. So it's a banded matrix with a bandwidth of 3, or also called tri-diagonal matrix. And then now, the rules of operation on matrix. So there are several rules that resemble a lot to usual rules of algebra. The addition and subtraction are commutative and associative. Commutative means the order of addition or subtraction doesn't really matter in matrix operation of addition and subtraction. And it's also associative. It means if you have more than 2 elements that you need to add or subtract, which one you do first doesn't matter as well. So that means that addition and subtraction of matrix are commutative and associative. And then multiplication. So we can also multiply a matrix by a scalar. Multiplying a matrix by a scalar means, let's say we have a matrix A multiplied by a scalar G becomes a new matrix D. A matrix D is simply a matrix with each element of A just now multiplied by the scalar G. So you multiply every and each element with a scalar G, that's the new matrix of D, which is G multiplied by the matrix A. Scalar G multiplied by matrix A. And what other operations can be done? Okay, the most famous, or the one that we use is multiplication or product of 2 matrices. Product of 2 matrices is represented by, let's say we have a new matrix of Z, which is a product of X and Y. So there are one important rules in order to make 2 matrices can be multiplied, X and Y. The rules is that the column dimension of X has to be equal to the row dimension of Y. So it is simplified here in this form. For example, if you have a matrix A with n number of row and m number of column, multiplied by a matrix B with m number of row and l number of column. So the number of column of the first matrix has to be equal to the number of rows of the second matrix. And then what happened is the new matrix, which is the product of A and B, is the matrix with a dimension of, so it takes the number of row of the first matrix and the number of column of the second matrix. It becomes n multiplied by m. So here we have a simple way to visualize how do we do the multiplication process, right? If you have, for example, here Z, which is X, the product of X and Y. X is a 3 by 2 matrix multiplied by a 2 by 2 matrix of Y, what we can usually do in multiplication easily is to put it in this form. So the new result would be, so for example, the element here would be 3 multiplied by 5. So let's see, we're going to come here. So 3 multiplied by 5 plus 1 multiplied by 7. So it becomes 3 multiplied by 5 plus 1 multiplied by 7. It becomes 22. So the first element of the matrix equals to 22. So let's say now it's 3 multiplied by 2, 3 by 2 multiplied by 2 by 2. So the result will be a matrix of a 3 by 2. So 3 by 2 means 3 rows and 2 columns. So 1, 2, 3, 1, 2, 3. So the first one is this, 22, comes here. And then you move to the second row and second column, second row and third row, and so on. First row, second column, and until you get the result as such, right? So this is just a review. We might as well do, I might give you some examples, some exercise for you to practice with in order to make sure that you revise well your matrix operations. So now rules on multiplication or product of matrix. So multiplication is not generally commutative, right? It's not commutative because we know that the number of column has to be equal to the number of column of A. It has to be equal to the number of column of B, and that's the only rules for it to be able to be multiplied, right? So for example, if we have A with a dimension of 2 by 2 and B with a dimension of 2 by 5, that means if now A multiplied by B can be done, but what if we do B multiplied by A? B by A means now we're going to do the product of 2 by 5 multiplied by 2 by 2. So now we see that the number of rows of the first matrix, which is now B, is not equal to the number of column of the first matrix now, which is B, is not equal to the number of rows of the second matrix, which is now the matrix A. So it is not generally commutative. It could be commutative in certain cases where the numbers can be multiplied, but in general it's not commutative. Matrix division. Okay, now it's something related to the inverse matrix or identity matrix. Matrix division is not a defined operation. It's not something that's defined. But for a square matrix A minus 1, so A minus 1 is analogous to A minus 1 is analogous to 1 over A, right? So if you have A, 1 over A, this is not a matrix. Imagine it's a number A. 1 over A can also be written as 1 to the power minus 1, A to the power minus 1, right? So this is what we call an inverse of A. So in matrix, this is not a defined operation. 1 over A is not something that can be done. It's not a defined operation. So what we can do is only a multiplication by its inverse. So what is multiplication by its inverse? Multiplication by its inverse is A minus 1, A to the power minus 1 is the inverse of A if A multiplied by A minus 1 equals to I. So that's where the identity matrix that I've shown you earlier is useful. So I, in order to remind, just a reminder, I is the square matrix of the same dimension, but with the only element that's non-zero is the diagonal element, and they are not 0 and equals to 1, right? That's identity matrix. And then the last thing is that what we call a transpose of a matrix. A transpose of a matrix noted by A to the power T, defined as mirroring diagonally the matrix, which means changing row to column as such. Right? Change the row and the column. All the row change into column. That's what a transpose of a matrix. So we stop for now and we'll continue in third part.